Okay, so let us start. Now, previous day, like yesterday only, we had our discussion till the different schedulings, the different job schedulings or process schedulings that we had. Now, after we come across the process scheduling, then we will have the idea of the process synchronization. Now, see, as we were discussing, that again people are giving attendance in the chat box, so I'll just suggest that don't write anything in the chat box. We will use the chat box just to calculate, means just to have your question and answer, right? So we don't need your attendance in the chat box. Fine. Now see, what do you mean by process synchronization? So what is a process? We have understood any instruction under execution, it is a process. Now when we come across the process is ongoing and more than one processes are sharing more than one resources, that is, if suppose I have a printer and from the email also I'm trying to print, from the Word document that is downloaded one I am trying to print, so which one will be using that printer at what point of time? So for that we have understood the job scheduling, the process scheduling. Previous day we had done the algorithms, like the names you must remember and what they do. The first come first serve, the shortest job first, preemptive non-preemptive both, then the priority scheduling, there also you have your preemptive non-preemptive both, and last you are having the round robin one where everyone is having equal time space, right? Just 1 second. Okay, so if now we have more than one resources which are being shared by more than one processes, right? So which one will be accessing the resource first? Is there any criteria? Or if more than one is trying to access the resources, then what type of problem they can face? Those things we will be studying, right? Now for that, the first thing that we have is the process synchronization. Now what is process synchronization? Suppose, see, these are very, very important concepts. So you must understand the concepts. Again, I am saying that this is not your like normal university exam where you will be given numericals to solve. But yes, here you will be asked to explain the concept at least, right? So what is process synchronization? We have studied multi-programming OS, right? So suppose if I have multi-programming, not multitasking, where the time slots are different, not that, multi-programming system, where suppose I have the number of processes active as P1, P2, P3 up to Pn, right? And I have my shared resources as suppose R1 and R2, right? So the processes cannot work on the resources in a shared mode. Like I was giving the example of a printer. So suppose I want to print from an email and I want to print from Word. So two processes are active, both are in ready queue. So which one will go first? Can both of them be done together? If you also give them simultaneously, then also one by one print will come out, right? That means they cannot work in shared mode, right? So both of them cannot be working together. Fine. So what is the consequence of this? there must be an ordering. So the fundamental thing is ordering of the processes that you have. So what is process synchronization? If I can do an ordering between my processes which are present in the ready queue, that which after which will come, that is what we call as the synchronization. At a time, all processes or more than one process cannot work, right? Now let us take an example. Suppose I have P1 and P2, two processes, and suppose I have one. P is the function which works both for P1 and P2. So resource A is being read, then A is incremented, and then A is updated. Right. Now if I go for case 1, where P1 executes first, right, then P2. Suppose this is my situation. Then P1 and P2 both are same thing, both are the same code. So once P1 is executing, by P1, the value of A is read. Suppose value of A is 10 at the beginning, right? So A is 10 read, then A equals to A plus 1. So 11 is written on A. Next, when P2 starts, P2 is having the value of A as 11, right? So 11 is read, then 11 is increased to 12, and that is written. So A is becoming 12. So that is my final value if I am running P1 before P2, right? Suppose in case 2, I go for context switching. Context switching concept you have already learned in DBMS also. So what is it? Suppose P1 is starting the execution, right? So suppose at this point, suppose P read of A, this is done by P1. So let me write it like this. This is suppose P1 portion, and this is suppose P2 portion. So after this, context switch happens, and then here P2 is executing. So P2 is also having the same code, A equals to A plus 1, and then update the value of A. There are semicolons, so I'm not just writing. After this, again context switch back, and then executing the rest of the part, A equals to A plus 1 and right of A, right? So this can be an example of context switching. Let us take the value of A is 10 at the beginning, like the previous one. So here A is 10, right? Next here, A has come as 10, A has become 11, right? So that is written by P2. Now P1 is now executing the rest of the part. So what P1 has read, P1 will work with this value only, because P1's cache is maintaining P1's read. So P1 is reading with value 10. Here P1 will be having value 11 at this point plus 1, and 11 will be written on the memory. So see here my final value of A is 11. And here my value of A is becoming 12. So the same two processes are working, different scenario. One is, the first scenario is one after the other it is happening. And the second one is, in between the process I am having the context switch. Now see, you can have the notion that P2 is writing 11 on the memory. So when P1 is next executing, P1 will get 11. But no, P1 will not get 11 this time, because P1 is using P1 scrap cache, right? So cache memory concept I hope you have. Previous day also we have discussed a bit. Now P1 is maintaining P1's data, where the copy of A is maintained as 10 because it has read 10. But P2 is maintaining A's data as the 11 here, right? So if it was 10 in P1, so it will increase and become 11. So same piece of code but shared variable, shared resource A, right, is having different values, or you can say different outputs for different cases, right? So this type of condition is named as race condition, where what is race condition? If you go by definition, you can find anything, means many difficult things, but what is race condition? Race condition is simply when the order of change of process can change the value of the shared variable. You can write it like this: when the order of change of order, change of process, or you can say instruction, is changing the value of output, it is named as the race condition. So here the order was first P1 then P2, and here the order is P1 then in between P2 then again P1. So change of order. So change of order is changing the value of A. A was produced as 12 in the previous case, and A is produced as 11 in this case, right? So this particular one is named as this particular condition where same set of instructions, but due to different execution, different things are happening, different outcomes are coming. So we call this as race condition, right? This is a very, very important terminology. Second one is critical section. Critical section, what is it? Again, you can find different definitions, but to be very simple, critical section CS, what is it? The shared resource which may undergo racing, or you can say race condition. So the critical section means that particular portion of your code where your shared variables are getting or going through value change, right? So that is your critical section. So whenever we are working, we will be trying to find out the critical section, and based on that we will try to arrange our ordering, right? So that is the critical section problem. Now see, if you consider P1 as an example, suppose I'm taking it from your book only. 2 into B. Suppose two processes are present, right? Two different processes. Who is the shared resource? Shared resource is B. B is the one who is working in both, so shared resources B for these two processes, right? Now see, if I number it, if I number the, you can say the instructions, just randomly I'm numbering. If the order, based on the order of execution, how many different values of B, the shared resource, you can produce? This type of questions are very common that you can face. Again, don't give attendance in the chat box. I don't require that. So, what is it? Based on the ordering of the processes or ordering of the instruction, how the value is changing, or how many different types of values we can get, right? So that can be a type of question. So suppose case 1, well, normally I am going for 1 2 3 4. Case 2, 3, 4, then 1, right? Case 3, 1, 3, 4, 2. Case 4, 3, then 1, then 2, then 4, right? All possible, more or less all combinations we will take. Case 5, 1, 3, 2, 4, and case 6, 3, 1, 4, 2, right? So suppose these many cases I can form. Fine. Now see how the value of the shared variable is becoming different. Now if I go by 1, 2, 3, 4, 1 means C is equals to, suppose the value of B is 2. Initial value of B is 2. So if I go for case 1, C equals to B minus 1, that means 1. B equals to 2 into C, that is 2. Then 3. 3 is D equals to 2 into B, that is 4. And B equals to D minus 1, that is 3. So from this case, you are getting 3. Fine. Please repeat the upper part. Upper part means this particular one. I have two processes, P1 and P2. There are lines of codes and the shared resource is B. Here the shared resource is B. So I am assuming a value of initial value of B, and I am trying to find out how many cases can be possible and what can be the possible values of B. Right? Now B comes under your critical section. Right? Shared resource which can undergo race condition, because if I do P1 and then critical switch or context switch, sorry, for P2, then the value of B can change. So that is what I'm trying to show, that how many values I can. Now 3, 4, 1, 2. So 3, 4, that means D equals to, initial value of B is 2. 4 means then 1, then 2. Right? 1, 3, 4, 2. 1 is C equals to B minus 1. 3 is D equals to 2 into B. Initial value of B is 2. 4, 2. So 4, B equals to B minus 1. And 2 is B equals to 2 into C. The final value of B is 2. Right? So likewise, if you execute the rest, case 4, 3, 1, 2, right? 1, 3, 2, 4. 1, 3, 2, 4. 3, 1, 2, 4. 3, 1, 2, 4. So you can see if I run by these cases, then the value of B can be either 4 or 2 or 3. So 3 types of values I am getting. That means if I have these two processes, then I can, if I go by sequence of ordering, like context which can happen from any instruction to any instruction, right? So if I have a shared variable and the value of the initial value is fixed, then if I undergo context switching, then these many values I will get, right? So this type of problem where more than one value is happening due to the change of ordering of the process, we call it as race condition. And the critical section means the shared variables value which is undergoing this change, right? How you are getting the values? Just by plus and minus. B is equals to 2. So the sequence is 1, then 2, then 3, then 4. So this is 1, then 2, then 3, then 4. This is my case 1. Calculate 1. C equals to B minus 1. So B is 2. So 2 minus 1 equals to 1. B equals to 2 into C. B equals to 2 into C. What is the value of C? 1. So 1. B equals to 2 into B. 2 into what is the value of B? Initial value was 2. Now the value is also 2. So 4. And what is B? B equals to D minus 1. So D is 4 minus 1. That is 3. Right? So likewise, we are just calculating the values of B in different cases. Race condition means suppose 1, 2, 3, 4 is normal. This is executing at first, then this one is getting. But if I go for 3, 4, 2, 1 is also normal. This is executing first, then this one. But what if I go for this case? 3, 1, 2, 4. If I go for this case, then 3 of this process is executing. Then 1 of this process is executing. Then 2 of this process is executing. Then 4 of this process is executing. So any process to any process can be switched by the processor. That is what your race condition is all about. And what is critical section? Any shared variable whose value is getting influenced by or getting varied by different race conditions is your critical section. Yes, B equals to 2 is constant for the two processes. B equals to 2 is constant for the two processes. Now, when you are changing from one process to the other, what is the value of final B? That is what I am trying to calculate. And by this means, I have shown you that if I do context switching, that is any process to any process, any instruction to any instruction, the value of B is getting influenced. Right? The value of B is getting influenced. So B can be called as a critical section problem. Right? Is it clear? What is race condition and what is critical section? Is it clear? I'm expecting some answers in the chat box whether race condition and critical section is clear to all of you or not, so that we can proceed towards our next type of synchronizations. Right. So the next type of question that you can face is about the criteria by which you can enter into critical section. Right. By suppose if I call the concept, we call it as the deadlock. Right. If I call the concept, we call it as the deadlock. So to achieve deadlock, we have to go via the conditions, right? 4 conditions. You have already studied them in your DBMS, but here also we will study. But before that, we have some typical critical section problems that we will try to solve. And using what we will solve, there is a very, very important term called as semaphore, denoted by S. So we will start learning what is semaphore and using this, how the values or how critical section can be controlled, right? So first let us understand what is semaphore. Semaphore is an integer which at first will be initialized with some value. which will be first initialized with some value. After initialization, it can be used using two functions. One is the wait function and one is the signal function. Understand this semaphore very well. What is a semaphore? Semaphore is a integer value that we will use to denote critical section or not, or any process who is going into critical section, we can avoid that problem or not. That is what semaphore is. So how it is used? It will be first initialized in your problem, and then it can operate into only two modes. One is wait of semaphore and one is signal of semaphore. Signal means the release of the wait phase, right? So when we call the problem of deadlock as hold and wait means what? If I have P1 and I have P2, P1 has got R1, P2 has got R2. Now holding R1, P1 is waiting for R2, right? And R2 is held by P2 and P2 is now waiting for R1. So whatever you are getting now, you hold that and then you will wait for something else. So when you are holding some resource, maybe that resource is requested by someone else. So there occurs your deadlock, right? So using semaphore, we will try to avoid that. Fine. So these many things you may not use for your concept, but means you can use for your concept, but no need to remember all these things line by line. Just understand that what we do using semaphore. We will discuss three types of problems which are very, very common in your critical section. And those will be how semaphore can entertain those problems that we will learn, right? So first, let us understand what is semaphore. Semaphore is nothing but just an integer which can be initialized or which will be initialized at the beginning of your program or anything what you are trying to do. And then it will be either using wait, it can be accessed, or using signal, it can be accessed. So we can either write it like this or we can write it like this. Now let us understand what wait does. By using wait, semaphore value is reduced by 1. And by using signal, semaphore value is released by 1, that is increased by 1. Understand the concept well. When you are using wait signal, wait of semaphore, you are decreasing the value of the semaphore by 1. And when you are increasing the value or you are releasing the semaphore, you are releasing the critical section, then you will increase the value of semaphore. So when you are entering the critical section, you will use wait of semaphore. When you will be releasing the critical section, you will be increasing the semaphore. Okay. Generally, we have the concept of binary semaphore. In all books and materials, you will find this. So semaphore value is either 0 or 1. Right? This is not 0 by 1. This is 0 or 1. Fine. So what now if you want to learn, or if you want to just have the idea what wait is doing, what is inside wait? We will directly write wait is, but what is inside wait? While semaphore is less than equals to 0, we will do nothing, right? So here you can write else s equals to s minus 1. So if the value of s is less than equals to 0, that means it has reached to the minimum level, we will do nothing. Semicolon means what? We will do nothing, right? Or else we will just reduce it by 1. This is the wait. This is what, if you write wait s, this is what happens. You may remember it, you may not remember it. This is just for your reference that what exactly happens. When the value of s is equals to 0 or less than equals to 0, less than equals to 0 generally don't happen, but we write because We are using binary semaphore, so it will be either 0 or 1. So if it is 0, we will do nothing. If it is 1, then we will reduce it to 0 because we are entering into critical section and I am following weightage, right? And signal does nothing but just a +1. So signal will do nothing. Whenever you call signal, it will just increase, right? That is releasing the critical section. Fine. So this is what your weight and signal is all about. This is what your semaphore is all about. Right now we will go into the critical section problems. So before that, just understand what your semaphore is doing. It is predefined or user defined. First of all, semaphore spelling is wrong. And secondly, it is semaphore generally by your operating systems, they are 0 or 1, means this is binary, right? In some cases where you have open like access to semaphore, generally it is fixed by your compiler, but means by your OS. But if you want to set it, then you have to set it separately as a variable, right? But the concept of semaphore is generally fixed as binary, that is that. Okay. So two things we can do using semaphore. One is waiting, that is when I'm entering into critical section, others will wait. They will get the value of semaphore as 0 and they will wait. And if they are getting the value of semaphore as 1, then they can enter into the critical section. Okay. Now, using the semaphore, the first problem that we solve is the producer-consumer problem. Producer-consumer problem. Typical problems, these are defined already. So how to solve them, that is what we will only use, means learn, right? Okay. So in producer consumer problem, there are two processes. One is the producer, one is the consumer. And there is a buffer of values. This is your shared resource. This is a buffer of values of size n. So your shared resource is having n sized value, right? So what is the concept? Producer produces and consumer consumes, right? So at a time, either producer can produce in buffer, whatever producer will produce, that will be added in the buffer, right? Or consumer consumes from the buffer. Understand the concept, the problem first. At a time, either producer or consumer can work. Producer will produce in the buffer. Whatever producer will produce, that will be added in the buffer. Or else the consumer will consume, that will be deleted from the buffer. Right? So this is the concept of producer consumer problem. Now see, the resource, suppose any one cell. In this cell, at a time, producer is producing and the consumer is consuming. This cannot happen because this is a shared resource. So either the producer will produce, the consumer has to wait, or the consumer will consume, the producer has to wait, right? So for that, what is the algorithm? I hope you have understood the problem, right? Now, first we will be defining the semaphores that we will use. So we will be defining a binary semaphore S. This is to take care of the critical section, that is your shared resource. Then you have empty set array, that is the buffer. At the beginning, everything will be empty, right? So E is equals to N. Understand why I am writing. At the beginning, everything will be empty. So empty set is equals to N. And once the producer is producing, it is named as, suppose, full set F. So at the beginning, nothing will be full, everything will be empty, right? So this is my initialization. This is my, right? So all of them are semaphores. This one is the binary semaphore, which is controlling the critical section, and others are we are using the critical section, right? For producer, so when producer is working, so two algorithms we will learn. One is when the producer is working, and another one is when the consumer is consuming, right? So when the producer is producing, what will happen? First, the S will be in wait state, because when the producer is working, consumer cannot work. Either or condition we have. So first, the semaphore has to wait, and then the value will be added, right? When the producer is starting to produce, the empty cell will reduce by 1. Understand? When the producer is starting to produce, that is, suppose if I start writing the algo, suppose I have to return nothing, so void produce or producer any function name, while true means having any value, I will start. I will call the produce function, right? Suppose then producer, what the producer function, what's the produce function does? It will be producing. Producing means what? The empty set will become -1. What this one does? E equals to N minus 1. If I initialize with N, E equals to N minus 1, empty set will reduce by 1. When empty set is reduced by 1, I am entering into critical section, because by this I am calling the critical section. This is my critical section, right? So by this, what I am ensuring, the consumer cannot enter to access your critical section, that is the buffer. Understand each line that I am writing, or else by yourself you will never be able to write. After this, wait test means I am adding some value. So suppose any random append function, then I will release the signal value. That means I am, what is this? This is adding value to critical section. Then signal S means releasing critical section. And then signal of F, because F has to increase. F equals to F plus 1. Here you better write E minus 1. Whatever the previous value of E, 12 minus 1. So second, E equals to E minus 1. Right? So whatever is your value of E was present, this will be reduced. Like N minus 1 I am writing correct, but initially it will be N. Otherwise it will be whatever is the value of E, that will be reduced. Right? F equals to F plus 1. Fine. After this, close the while function, close this. So this is for your producer. Understand what I am doing. Producer is calling the produce function that will be doing a plus in your value. So empty set was at the beginning, everything is empty, right? And full slot is equals to 0. That means nothing is full, everything is empty. So first I am doing empty, producer is producing, right? Producer is producing. So empty set is reducing, everything was empty. So empty set will reduce, right? I will introduce something. So if suppose I will write a value 5 here, that means this cell is now becoming full, right? So empty set is getting reduced. Then I access the critical section. So wait is, so consumer cannot enter at this time. Then I append any value. Suppose I enter 5. Then signal of S means I am releasing my critical section because I have already appended a value. Then signal of F, that means the full set will be plus 1. One value I have inserted. So full set will be plus 1. This is the producer function, right? Producer value. Have you understood that how using semaphores I am accessing the value and how I am restricting the consumer to access the value? Similarly, I will be doing it for consumer. Okay, just let me increase the page. One minute. Okay, so for consumer, what will happen next is for consumer. For consumer, what will happen? When I am in the consumer section, I will expect that all the values means the full set, the full value, whatever I was having will be decreasing by 1. So let us first write void consumer same while true condition. Then only I will enter. So consume. Suppose this is my function, any function you can use. Who will reduce? Consume means what? I am deleting something, so full set will be reduced. Right, so what it means? Full set will reduce. I am deleting from the full set, right? The full set will decrease. Then I am acquiring the critical section. Then you suppose take delete function. You want to consume, so you delete. Then you release. Wait S means producer cannot access. Producer cannot access the critical section. When I am writing in consumer algo, when I am writing the wait S, that means consumer is acquiring the semaphore. So producer cannot access. Sorry. Producer cannot access the critical section. Then I am deleting some value. Then I am releasing my critical section. Then empty set, one set has become empty, right? So empty set is done. After that, if you want, in some books you will find after this you have use. So the value that you have extracted, that one you are using. So that is very nominal. So I may not say it here, but that is your release, right? So consumer is consuming means from the full set, the consumer is deleting any one value. So the full set will reduce by 1 and the empty set will be plus 1. Right, one set is getting empty, so 1 is the plus 1, right? So this is what your producer consumer problem is all about. And using semaphores, we are having the value, means we are acquiring some value which others cannot use. Ma'am, in the last step E is increased by 1. Yes, here empty set means increasing by 1 because I am deleting one value. That means empty set is becoming more If you are deleting one value, that means what? More are becoming empty. So empty equals to empty plus 1. Right? So this is very, very important. All critical section problems are important to be asked questions from. So the first one is producer consumer problem that we have discussed. Have you understood? Algos and these things you may not mug up. If you understand, you can write it on your own. Right? Have you understood? Yes, no? If no, then which portion you have not understood, please ask. This is your producer. This is your initialization phase. This is your producer phase, and this is your consumer phase. Right? E portion I did not understand. Which portion? C, consumer or producer? In consumer, you did not understand E. Okay. Suppose you have, this is your n size buffer, right? Suppose you have 5 here, 6 here, 2, 7, 11. Right? So I will be deleting this particular value. Right? So I will be deleting this value. So total critical section I have taken by this weight of F. That means it was full. So F was equals to 1, 2, 3, 4, 5. So I am deleting one place. So F is equals to F minus 1, that is 4. Right? What was E at this point of time when everything was present? E was 0 because all are present, right? So E is equals to 0. So whenever you are deleting this value, this place is becoming empty, right? This place is becoming empty. So E was 0. Now E will become plus 1. Signal means what? Plus 1. Right? So equals to E plus 1. So now after deleting this this 5 place, 7, 2, then vacant, then 6, 11. So that means what? Full set is 4. 4 places I have the values, and empty place is just only 1. So 1. Right? Did you understand? Yes, weight is S is for critical section. To acquire the critical section, we use weight S. To release the critical section, we use the signal of S. Right? Okay, so any more problem? I don't think so there is any more problem. So we can proceed towards the next one. Do you have any problem? আর কিছু জিজ্ঞাসা আছে এখান থেকে? Any questions from this particular producer consumer problem? The entering, sorry, I missed the question. The entering and releasing state is locking and unlocking, and wait part is busy state. No, it is not about locking and unlocking. We are not locking data. We are just acquiring that section. That suppose I am going to CCFL to take the lab. So at that time, if the lab of suppose EC people, at that time if CSE people come, then the lab is occupied, right? That means what? You cannot do the lab there. So I'm not locking it, but I'm just acquiring it for my use. Right? So when I'm taking the lab, do I lock it? No, I'm just taking the class there. Same thing, I'm working there, and hence no one other will be entertained. Right? So that we are using the binary semaphore. Okay? Okay, so we will go to the next one now. Next one is the reader-writer problem. Okay, another critical section problem. We call it as the reader writer problem, right? So in reader and writer problem, we have two processes. One is the reader, one is the writer. And what is my critical section? The text which I am either reading or writing, that is my critical section, right? What is the condition? Now understand the condition very well. The condition is dependent on the conflict. You have learned database, so now it is easy for you to understand while writing. Now see, write can have conflict with both read and write. And read can have conflict with only write, not read. Read does not clash because read is not updating any value, but write with clash will anyone. So while writing, I will do an weight of S. So no one can access my critical section when I am writing. While reading, this is one condition. Second condition, while you are reading, read condition is allowed because read does not clash. Write is not allowed, right? So understand the conditions. Condition number one, when you are writing, you will not allow anyone. So while writer, I will just use wait S. And why after I finish my writing, I will release signal S, right? So while writing, I don't have any problem, but while reading, I have severe problem, right? So while reading, only read is allowed. If I have a read function, then it will be allowed. But if it is write function, suppose one text can be read by 5 people at the same time because they are not updating the values. But if I am reading and someone else is asking for write, then that will not, strictly not allowed. Right? I hope you have understood the condition. Condition ta বোঝা গেছে? Have you understood the condition? Yes, no, anything? Have you understood the condition? Right? Now let us start the initialization. This was our condition. This is our reader writer section. Now first is initialization. Okay, so what things we will initialize? Suppose semaphore is right. Semaphore is WRT. So when WRT is wait, then no one will be allowed to enter. Other than that, we have a mutex, that is another semaphore suppose, and we have a read count, which is equals to 0 initially. Read count means we will be using that how many readers are reading. More than one can, right? So we will just do plus and increase them. Okay. Now, if I do it for writer, it is very, very simple. Wait WRT here is my semaphore. So wait WRT, any name you can give or else you can use S. No problem. Write operation, whatever you have. And then, so for writer, it is easy, right? Now if I go for reader, you have understood, writer means I am taking a right semaphore. I am taking a right semaphore, and that right semaphore is doing what? While I am started my writing, then it is just getting the other's weight. This write means reader, writer, all has to wait, right? So when I'm doing write, weight of write, that means any other process who is trying to enter, that can be reader, writer, anyone, everyone has to wait strictly. But in case of read, release of text, right? The critical section. In case of read, we have to do it a bit of complications, right? So for readers, more than one reader. If a reader is inside your critical section, if a reader is in critical section, then allow reader read counter plus plus, right? So your mutex that you have, if my mutex is equals to 1, if my mutex is equals to 1, that means I can allow readers. So I can say mutex is used to synchronize between the readers. Okay, and if I have mutex is 1, then read count. Okay. So suppose mutex 1 is my initialization. So by weighting of the mutex, we can allow the readers, right? So first case, when I'm entering. So reader is entering, so read count plus plus. If my read count is 1, that means one reader is at least inside. This means the first reader is inside, is in critical section, right? Writer will not be allowed. When the reader is inside, other readers are allowed. But when the first reader has gone into the critical section, writers not allowed. Fine. Next, when you are releasing the readers, wait, mutex. Now you are releasing the reader, read count minus minus. If there is no reader, that means read count is equals to 0, then you can allow the writer. So signal write, and then you allow your mutex. Okay. So this is the exit of readers, and this is entry of readers, right? So this is entry and this is exit. Now understand what I am trying to do. Read count is initially at 0. When the first reader is entering, that means mutex wait, that means the first reader is means entering. So when the first reader is entering, I am doing read count plus plus. That means if it was 0, it is 1 now. That means at least one reader is inside. So if one reader is inside, I can do anything with the readers, but writers need to be prohibited. They will not be entered. So weight of right. Okay, so right is prohibited then. After that, when I'm releasing my reader, the writers can enter. So when my read count is minus minus, and when it reaches to 0, this means what? Last reader has left. So after that, I can allow my write. Fine, so signal write. Okay. I hope you have understood this reader writer problem. Writer, we don't have any problem because when I am in writer, only the write operation is allowed. No one else is entertained. But when I am in reader, read count can always increase. But whenever read count is becoming at least one, that means at least one reader is inside. That means other readers will not be entertained. Sorry, other writers. Sorry, other writers will not be entertained. Okay. What is the function of semaphore mutex? Mutex is indicating whether you can allow readers or not. Whether you can allow readers or not. Wait mutex means the first reader is already inside. So read count is plus for us. I have written here allow readers. Mutex, by mutex, I'm allowing readers. More than one reader is allowed. So read count can be anyway plus plus. Signal mutex means I'm releasing the reader. Releasing the reader here. Again, if I acquire the reader, if there is reader section, but reader is being released, count minus minus means the last reader is also leaving equals to 0. Here I am entering the section. Then I am increasing the reader because reader has entered. When the read count is 1, at least 1, that means any one reader is inside, so writer won't be allowed. So restrict the writer. Then you can release the reader or you may not release. Right? So this is the reader's entry section, this part. Then when you are releasing the reader, so wait mutex synchronizing the readers. Wait mutex, if you don't do, you cannot release or allow any readers, right? So wait mutex, then read count is minus minus. That means the reader is leaving, right? So when it is becoming 0, you can allow the write now. So signal of write. Okay, then signal of mutex. Mutex will only control the reader side. For writer, it is wait write. You can see here. Wait write means I am controlling the writer. Signal write means I am controlling the writer. Mutex is only for reader. Right? So this is your second critical section problem. Reader writer problem. Okay. I hope it is clear by now. Okay. Next one is okay. So next one that we have is the dining philosopher's problem. Okay, dining philosopher's problem. Now in dining philosopher's problem, we have another critical section problem. Okay, so if I consider a philosopher, then philosopher will have only two processes. One is eating and one is thinking. Philosophers, right? So they think and they eat. right? Other than that, they will do nothing as per the problem. So here we have 5 philosophers, right? And they are sitting in a circular table, right? At the center of the table, there is a bowl of food, right? Food or something, anything. There is a bowl of food which they will eat, right? And beside each philosopher, we have one chopstick. So there are 5 chopsticks, right? So the situation is like this. If this is my bowl of food that I have 1, 2, 3, 4, 5. 5 philosophers. They are having, each of them is given with one chopstick. So 5 chopsticks, right? So this is my situation. This is my situation that I have written. Fine. Two processes, philosopher processes are 2 processes. We have either eating process or we have thinking process. Fine. Philosophers are arranged around the circular table. In the center of the table, they have the food that they will eat while they will not think, right? And we have 5 chopsticks, right? Now the criteria, so this is the situation that I have drawn. Now the criteria is each philosopher will need 2 chopsticks to eat. Those who of you who know the function of chopsticks, so you will understand, like spoon and fork, right? So each philosopher will need 2 chopsticks to eat. Sorry, this is not end, this is eat. Right? Now the problem will arise. Suppose this is philosopher number 0, this is 1, this is 2, this is 3, this is 4. Right? Again, if I go by chopstick numbering, this is 0, this is 1, this is 2, 3, 4. Suppose number 4% philosopher wants to eat. So it requires 0 and 4 both. At the same time, if 3 also wants to eat, it can get 3, but can it get 4? No, 4 is already occupied by philosopher number 4. Understand the problem. 2% who are sitting who are sitting side by side, if both of them want to eat, then it becomes a problem. So here my critical section is the chopsticks. Now understand, if I say critical section is chopsticks and you think that number 3 will get like jump on chopstick number 1 and start eating, that is not allowed. So whatever chopsticks are nearby to them, they will use them only to eat. They will not go for another one. So if chopsticks are not available, they have to wait. Fine, that is what the idea is. So it is a type of hold and wait problem. So I was talking about hold and wait. Suppose this number 3%, this person has got the number 3 chopsticks free. So this person takes up number 3, but number 4 is not free. So that means it is holding number 3 and waiting for number 4 to get released, and it will then start eating, right? So this type of problem is named as the hold and wait problem, right? Now, what next we will do here? Here the problem is a bit different. So for every chopstick, I will assign one semaphore, right? Because here my critical section is, there are 5 critical sections, right? So semaphores. So this is my 0th chopstick. This is my 1th chopstick. This is my 2th chopstick. This is my 3th chopstick, and this is my 4th chopstick, right? So 0, 1, 2, 3, 4. 4 chopsticks I have, and every one is denoted with a critical section, right? Suppose at the beginning, everyone is to wait state, understand it very well. When your semaphore number 0 and semaphore number 4 is going under your chopstick, your philosopher number 4, right? Then they are becoming in wait state. At that time, the other philosophers can start eating who are not sharing their chopsticks. They can start eating. So if I deal with number 4 and number 0 at a time, then number 1, 2, 3 are fine. So if suppose at that time, this number 2 person is trying to acquire 2 and 3. So I can see 2 and 3 both semaphores are available. So they can eat, right? So there is no problem. Now, so how we will be writing here, how we will be denoting our algo? Suppose I am into my thinking process. I will not do anything. When I am acquiring one chopstick, so you name it as chopstick of I, right? So you acquire that. Next, you will ask for, that is, you will wait for the next chopstick that is around you. What is that? I plus 1 mod of 5, and then only you can start eating. After that, you will release them. Now see this modular 5. Suppose you need the, you are the 4th philosopher, right? So number 4 chopstick you have already assigned. What else chopsticks do you need? You need the 0th chopstick, right? So for 0th chopstick, what you will get? If I don't do this mod, now most of you will ask the question that why you are doing mod 5? We can just do plus 1, right? So if I do plus 1, this will be 4 plus 1 equals to 5. Do you have a 5th chopstick? No, you have to get back to 0. So that I am doing this modular of 5. So 5 module 5 is equals to 0. So this person, this 4th person, when my I is equals to 4, I am acquiring the 4th chopstick and I am acquiring 4 plus 1 modular 5. That is your 0, because you don't have the 5th chopstick, right? And after that, what you will do? You will just release them. So signal of chopstick I. So you release the 4th one, and similarly, you will release the 0th one once your eating is done, because eat function I have already implemented, right? So I'm just releasing, right? So this can be your sample process of thinking and eating, right? While you think, I have put in a semicolon because while you are thinking, you are doing nothing with the chopsticks, right? So you cannot keep the chopsticks waiting. But when you are eating, before that, you have to make the chopsticks acquired. So here you acquire the critical section. The chopsticks that you require are your critical section, fine. And after you finish your eating, you are releasing your critical section, right? Again, suppose I am the third philosopher. So I will be acquiring that I'm the third philosopher, right? So I will be acquiring which ones? I will be acquiring 3 and 4, right? So chopstick of 3, I equals to 3, and 3 plus 1 by 5. That means 4. 3 plus 1 is 4. So 4 modular 5 is what? 4 is not divisible by 5. So modular is 4 only, right? So third and fourth I have 4. So this is my dining philosopher's problem. Right, so this is your sample section. Right, so again, just briefly, dining philosopher's problem, two processes are ongoing. One is eating process, one is thinking process. Right, so while I'm eating, I'm not allowed to think. While I'm thinking, not allowed to eat. Mutually exclusive. Next, I have 5 philosophers in my problem who are sitting around the round table, circular table. Right? In the middle of the table, there is a bowl. While I am trying to eat, I will be using sticks. Now, every philosopher on their right hand side, suppose they are having one chopstick each. But using one chopstick, I cannot eat. Fine, I need at least 2. So I will be obviously taking the nearest ones to me, nearest chopsticks. So here my critical section are 5 chopsticks that I have. Everyone targeting their side chopsticks, right? The sideways, whatever chopsticks are written. So I have numbered the chopsticks, I have numbered the philosophers. Next is, here I cannot use only one semaphore because I have 5 different critical sections, right? So 5 semaphores I have marked here. Nice. Now I have named them also. Now, how I will be using it? When I have one chopstick, if I'm waiting for the other, that is a hold and wait process for deadlock, right? So until and unless the other person is releasing that holded one, I cannot eat. But how to acquire both? I will use wait. Now, when wait signal is being used here, wait will be applied twice on both sides of my chopsticks, right? So if I am the ith philosopher, I can be 1, 2, 3, 4, 0 at anything. I will be acquiring the ith chopstick and I will be acquiring the I plus 1th chopstick, basically. But I plus 1 has a problem because when I am the 4th philosopher, I do not have the 5th chopstick here. So I have to acquire the 0th one. When I'm the 4th philosopher, I have to acquire the 0th one. It's a round table, right? So we are using this modular of 5. Okay, so that I can go back to from 4, unless I am going to 5, I will go back to 0. Okay. This is your dining philosopher's problem, and using semaphore, this is how we are solving. Is it clear? Or if you have any problem, please ask. Is this clear? Is this clear to everyone, those who are present? Okay. Okay, so next the thing that we will just go through once is the deadlock and its condition. So deadlock more or less we know. Suppose I have 2 processes P1 and P2 and I have 2 resources R1 and R2. So P1 is already holding R1, P2 is already holding R2. Now P1 cannot proceed without R1, so it has R2, so it has requested and this is waiting for R1. Right, so this process, until and unless one leaves both the resources, then only the other can work. This is your deadlock situation, right? In this scenario, there are 4 conditions and Even if all four are true, all four are true, then only deadlock will happen. When all four are true, then only deadlock happens. So let us just go by the names. Mutual exclusion, hold and wait, no preemption, and circular wait. Mutual exclusion means if any type of resource which is available to everyone and there is no conflict. Suppose if I talk about an YouTube video, or suppose this Zoom meeting, this is accessible to all participants present. So there is no like I will do, then you will do, nothing like that. If I get your lab file signed, suppose, then one by one only I will do. But if I am trying to teach something, then in general I can just teach. If you have any problem, then one by one I can solve, right? So that is mutual exclusion. If you don't have mutual exclusion, then you can have deadlock. Once I am sharing with someone, then only I can have deadlock, right? Next is hold and wait. Suppose I say that I want 4 pens. Now I have got 3, and now I am waiting for the 4th one, right? So suppose I am not using all 3 because I am not started the process, but I am just holding those 3 which I have got, and I am waiting for 4. Now those 3 pens, if I have just hold on them, and I'm just waiting for another one, suppose among these one is requested by other. If I am not using them, let me release. Others can use them, or else it will be a deadlock, right? Next one, no preemption. Suppose in this case, P1 is using R1 and P2 is using R2, right? So in this case, if P1 requires R2, let us forcefully stop P2. That is preemption. We have studied yesterday. Preemption means I am forcefully stopping it, right? So if I can forcefully stop this, then I can work with R2, right? So there can be your means if I cannot forcefully stop, then deadlock will obviously happen. I have to wait for infinite time, right? Next is the circular wait. Circular wait means if this is also same thing. P1 is a kind of circular wait if you write, right? So one is for waiting for another one is waiting for another, and the last one is waiting for the first one. Then we can say that this is a circular wait. So one is waiting for the another, and likewise the cycle forms. If you cannot break them, then deadlock will happen, right? So any of these, if occurs, then there is a chance of deadlock. But if deadlock is there, then all 4 must be true, right? If there is no mutual exclusion, deadlock can happen. If it is hold and wait, like I'm holding the resources which I've got and waiting for the others, then deadlock can happen. If I don't have the provision to forcefully stop any process, then no preemption will happen, like deadlock can occur. Or I have to go for starvation. Like here you can get introduced with the term starvation. What is starvation? Starvation means if one process is waiting for another and likewise it is waiting for infinite time, then starvation can occur. Okay. So what is starvation? If I am not getting the resources that I am supposed to get to complete my work, then starvation can occur, and starvation will create the deadlock. Right? It will means one by one process like starvation will happen, and then only deadlock can happen. Like So to work with deadlock, we have deadlock prevention, deadlock avoidance. So in case of what is prevention? Prevention means I will do the allocation such that deadlock will not happen, right? And deadlock avoidance means some measures I will take so that we can avoid deadlock. Starvation means if suppose P1, P2, P1 is working on R1 and P2 is requesting for R1. Now, if P2 has to wait for infinite time, then it goes into starvation. Suppose before P2 acquires R1, P3, another process comes and acquires R1. So then P2 has to wait for the time P3 also completes, right? So there can occur starvation, right? So deadlock prevention and deadlock avoidance. Now, we have the resource allocation algorithm based on the availability and the requirement. We call it as the banker's algorithm. So it's a deadlock prevention algorithm where the availability metrics and the request metrics are to be mapped, right? So today we have like reached the end of the time. So next day we will start with this and then we will do the memory management, right? So from the last few portions, do you have any questions? Then you can ask or else we can end the class. Okay, then if you don't have any questions, then we can just sign off from this class and your next class will begin at 12. Okay. Okay, thank you for attending. See you in your next class tomorrow.